Welcome. Today, we are diving deep into the absolute building blocks of our universe. Seriously, we're going to journey from a simple idea right to the very heart of matter itself. So, let's get into it.
It's one of the biggest questions you can possibly ask. From the stars burning billions of miles away to the device you're watching this on right now, what is all this stuff really made of? Well, the answer is both incredibly simple and just mind-bogglingly complex. And it all starts with one concept: the atom. It is almost impossible to wrap your head around just how small atoms are. But think about this for a second. That tiny little dot at the end of a sentence in a book, it contains several million atoms. Wow. They are the completely invisible foundation of our entire world. So what even is an atom? Okay, imagine this. You've got a pure gold bar. If you keep cutting it into smaller and smaller pieces, the atom is the absolute smallest piece you can possibly get that is still fundamentally gold. Any smaller, and it's not gold anymore. It's the basic unit of an element. So our modern idea of what an atom is really took a giant leap forward back in the early 1800s, and it was thanks to an English scientist named John Dalton. He came up with a theory that would basically become the bedrock of all modern chemistry. Dalton's theory gave us three foundational rules. First, pretty straightforward. Everything is made of atoms. Got it. Second, all atoms of one element, say iron, are identical to each other, but they're totally different from the atoms of another element, like oxygen. And third, and this is a big one, atoms don't just randomly mix together. They combine in simple, whole number ratios, like 1-to-1 or 2-to-1, to form all the compounds we see around us. For a long time, we thought atoms were the end of the line. I mean, the name atom even comes from a Greek word that means indivisible. But turns out, we were wrong. Atoms themselves are made of even smaller, or subatomic particles. So now, let's take a journey inside. So, inside pretty much every atom, you're going to find this cast of three characters: the proton, the neutron, and the electron. These three are the essential components that give every atom its own unique set of properties. Okay, so how are these guys different? Well, protons have a positive charge, electrons have a negative charge, and neutrons, you guessed it, are neutral. But the real shocker here is their mass. Check this out. Protons and neutrons are the heavyweights. They have roughly the same mass. The electron, though, it's incredibly light. We're talking almost 2,000 times less massive. And that difference is absolutely crucial for understanding how atoms work. So where do these particles actually live inside the atom? Well, thanks to some brilliant experiments by a guy named Ernest Rutherford, we know they're not just jumbled up. The heavy particles, the protons and the neutrons, are all packed together in this tiny, super dense center called the nucleus. And those lightweight electrons, they're zipping around in the space orbiting that nucleus. All right, so we know the parts and we know the general layout, but how do these components actually define what an element is? What makes gold different from lead, or what makes oxygen different from helium? It all comes down to one single number, the number of protons in the nucleus. That's it. We call this the atomic number, and it's like a unique, unchangeable ID code for every single element in the universe. For instance, if an atom has just one proton, it is always hydrogen, no exceptions. If an atom has 26 protons, it is always iron. If you could somehow change the number of protons, you would literally change the element into something completely new. Now this might sound like a trick question. I mean, if the number of protons defines the element, how could two atoms of the same element ever be different from each other? Well, it turns out there's another particle we have to think about. And the answer is something called an isotope. You can think of isotopes as just different versions or flavors of the same element. They have the exact same number of protons, so chemically they're the same, but they have a different number of neutrons. This changes their mass, but it doesn't change their identity. It's why we have things like carbon-14, which is just a heavier version of carbon that we can use to date ancient artifacts. So this brings up a new puzzle, right? If an element can exist in different versions or isotopes, and each one has a slightly different mass, how in the world do we decide what the mass of that element is? How do you weigh something that's not only tiny, but also comes in multiple varieties? Well, here's the secret. The mass that you see on the periodic table isn't actually the mass of one single atom. It's what we call the atomic mass, and it's a weighted average based on how common each isotope is out in nature.
Let's make this real with an example. Take the element boron. In nature, it mostly exists as two isotopes. About 20% of all boron is boron-10, and the other 80% is boron-11. So to get that weighted average, we just take the mass of each one and multiply it by its abundance. So we'll take 20% of 10 and 80% of 11, and then just add those two numbers together.
And when you do that quick bit of math, you get 10.8 atomic mass units, or U. Now, the cool thing is that no single boron atom actually has a mass of 10.8. It's just the average of the whole population of boron atoms out there.
Okay, let's zoom back out a bit. We figured out the identity and mass of individual atoms. But in the real world, atoms are social. They rarely hang out by themselves. They link up, they bond, and they form molecules. This creates a whole new challenge. How do we give a unique name to every possible combination? Well, luckily for us, chemistry has a really beautiful and logical system for that. For simple compounds made of just two elements, the naming system is basically a two-step recipe. Step 1, you just say the name of the first element. Easy enough. Step 2, for the second element, you use a special prefix, then you take the root of the element's name, and you slap the suffix "-ide on the end. Let's look at those prefixes. These prefixes are the secret code that tells us how many atoms there are. So mono is for 1, di for 2, tri for 3, and so on. Once you know these, you can basically decipher the recipe for a huge number of molecules.
All right, let's put this into practice. Let's take the molecule SO3. The first element is sulfur. There's only one, so we just say sulfur. The second element is oxygen, and there are 3 of them, so we use the prefix tri. Then we take the stem of oxygen, which is ox, and add the "-ide suffix to get oxide. Put it all together, and you get sulfur trioxide, a unique name for a unique molecule. See? Simple.
Okay, let's do a quick recap. We've learned that all matter is made of atoms, and inside them are protons, neutrons, and electrons. We know an element's identity is totally locked in by its proton count. That's its atomic number. We learned that isotopes are just different versions of an element with more or fewer neutrons, which is why atomic mass is a weighted average. And finally, we saw how there's a really logical system for naming the molecules that these atoms build. And there you have it. It's just incredible to think that from just 3 tiny particles and a few simple rules, the entire material world gets its structure. Everything from a grain of sand to a distant star. It really makes you wonder, what will you build with this knowledge? Thanks for joining me on this deep dive.